Right, welcome back everyone. For the next lecture, we have Professor Sayak Ray Chaudhary from IIT Kanpur. Sayak did his PhD from the EC department right here at IISc and followed this up with postdocs from Boston University and at Microsoft Research Bangalore. His work primarily is in theoretical machine learning and with focus on sequential decision making and differential privacy. And today and over the next 3 days, he is going to give us an introduction to differential privacy. So join me in welcoming Professor Sayak.
Am I audible? Can you guys hear me? Yes? Thanks for inviting me to give a lecture on differential privacy. It's been a privilege to come here where I did my master's from this department. And so for today, tomorrow and day after, I will give you a brief introduction to the concept of differential privacy. About me, I am an assistant professor at IIT Kanpur in Computer Science Engineering Department. As Aditya mentioned, that I work in privacy and sequential learning algorithms. Okay, let's start. So this is the content of the course. So we'll start with the overview of data privacy. What is data privacy, and how come we overcome the problem of data privacy? The first thing that we will look at, why do we need privacy? So next we will go to the topic, how can privacy be breached by some attacker or an adversary? And then we will talk about adversarial attacks on informations that are computed from private data of individuals. Okay, so after discussing the problem of data privacy and why do we need privacy and discussing different kind of attacks, we'll show that differential privacy is a viable answer of this problem. So we'll start with giving definition of differential privacy. Then we'll talk about some properties of differential privacy. And then we'll go to algorithms which achieves differential privacy, and we'll talk about the privacy and utility guarantees. Okay, and then finally we'll go to differential private algorithms. We'll probably possibly focus on an application to machine learning. Okay, so feel free to ask questions whenever you have some doubt. Let me give some acknowledgement first. So the materials are based on, it's been sourced from couple of, sourced from this book by Algorithmic Foundations of Differential Privacy, written by Cynthia Dwork and Aaron Roth. And a lot of slides are based on courses taught at different universities. Specifically, this course, Privacy in Statistics and Machine Learning by Adam Smith and Jonathan Ullman in Northeastern and Boston University. Similarly, Privacy Preserving Machine Learning, it's a course taught by Aurélien Bellet in a summer school. Also, some of the materials will be based on courses by Professor Gautam Kamath at University of Waterloo, and also courses taught by James Honaker and Salil Vadan at Harvard. The course name Applied Privacy for Data Science. So these 4 courses I will recommend you to go over their slides and videos are in online. I will recommend you to go over these courses. And for a beautiful introduction of differential privacy, this is a good textbook to follow. And I'm teaching this course for the first time. So, in fact, I'm teaching for the first time. So, pardon a lot of mistakes, a lot of blabberings, and suggestions are welcome. Okay, so what is data privacy? It's an ability of an individual to seclude themselves or to withhold information about themselves from the rest of the world. This is data privacy. So why data privacy is now important in today's era of big data and machine learning and artificial intelligence. And The reason is data are now present everywhere. So massive collection of personal data by companies and public organizations, driven by the obvious progress of artificial intelligence, ML, and data science. Companies like Amazon, Apple, Facebook, Google, Uber, Waze, we use these products, their products, every day. So our data is getting collected by them every now and then. Not only that, our governments also collect our unique personal information. Not only governments from different countries also collect personal information of their citizens. And this data collected by the governments are increasingly sensitive and very detailed personal information. For example, if you searching in Google the browsing history, they stored your browsing history. Amazon stores your purchase history. Facebook knows about your social network posts. Uber has your locations of travel. Similarly, the US Census Bureau collect health information. Our other system collect our personal informations. All right. Now think about machine learning that is using our data all the time. Consider this application, real-time speech translation. So when the speech, so suppose I am speaking it in English and it gets translated to Hindi. So a system takes my voice or a speech and then goes to several procedures to translate to Hindi or some other language, and so my speech or my voice is getting recorded and getting stored in the system. Similarly, consider the application of autonomous driving, where self-driving cars are there. So wherever these things are used, so the locations, the routes that we are taking every day can be stored in the company's website, company's storage systems. Okay, in the third example, consider your Amazon, where recommendation or any recommendation systems where collaborative filtering or content-based filterings are used to recommend products to users. So here, consider this collaborative filtering example. So there are say two similar users, and these two documents are read by both the users. And since these two users are similar, if one document is read by one user, the recommender engine recommends the same document to the similar user. Okay. Similarly, think about content-based filtering. If a user read some particular document and then there are a lot of similar articles of that particular document, so the recommender system will also recommend the same document to the user. So what is getting captured here? The user's, purchase history or browsing history or document reading history. This sensitive information getting captured here. Similarly, now we are in the era of AI. ChatGPT is everywhere. Probably everyone is using ChatGPT. We are conversing with ChatGPT, and as we all know, a lot of private informations or sensitive informations are sometimes also coming up from these systems in the open, right? So as our data is getting used by machine learning algorithms more and more, so our data protecting the privacy of our data is much more important in nowadays. And obviously we know that sometimes data gets sold by some malpractitioners. Our sensitive data gets sold by some malpractitioners. Alright, so this is the big problem in today's world, how to protect our data from getting sold. Like if it will get sold, how to protect our sensitive information so that even if the data gets sold, our sensitive information is protected. Alright, now let's think that how data is getting collected in a system. Okay. So when you visit a system, visit a website, there are a lot of tracking files which actually watching what you are doing online and developing a profile based on your behavior. Like your behaviors could be, your shopping history, what about the things you are browsing, okay? And as you know, it gets stored, your profile gets stored in this storage, systems, and what an advertiser of a tracking company sells this information directly to these advertisers, so that the advertisers take this information and can recommend some product, maybe a book or a car to you, and you see, okay, this book I liked, or this car I liked, or it might affect your purchase behavior. So far so good. So advertisers are paying money to these tracking companies, and advertisers are using this to improve their profit. But suppose some sell your data on some exchange, right? In data exchange, some malpractitioner sell your data on the exchange, and this can be combined with some other sources of personal data and be sold to advertisers looking for consumers like you, or some attacker or some adversary. So this is the overall pipeline of data is getting collected, and advertisers are using that data, and sometimes attackers or malpractitioners can also have access to your data. Alright, there are a lot of websites like that which actually track our data, and there is a study which did some exposure index, which website, how many trackers are tracking our data. There are some websites where the exposure index is very high, some are medium to high. So as you see that our data is getting tracked also. Alright, now think about a machine learning problem. So we are solving a classification task. There are two classes, a positive class and a negative class. Both the classes are linearly separated by this hyperplane. So what is an algorithm for classification? What is the basic algorithm for classification? Any guesses? SVM, right? So say SVM. What does SVM do? It finds the minimum margin hyperplane among all these hyperplanes, right? Say this is the minimum margin hyperplane. So why it is a minimum margin hyperplane? So you will look at both the classes, class 1 and class minus 1. So this point, take this point and take this point. This line clearly bisects these 2 points in an equal direction. So this line is a minimum margin hyperplane. And do you know what these 2 points in this dotted line signifies? Support vectors. So this is a support vector, and this is another support vector. So if the algorithm returns these 2 points, it will return this hyperplane. So to answer the machine learning model, which is a support vector machine, it only needs to return these 2 points, this this red point and this green point. So now think about what are these 2 points. These 2 points are training data, and the machine learning algorithm is returning this to training data as its output, right? And think about, this is your personal information, your data. So your data is getting outputted by the algorithm itself. Okay, so now if an attacker does see the output of the algorithm, it knows basically your data. So your data is getting leaked on the open by output of the algorithm. Okay, so here the support vectors actually revealing the training data.
Just to check, the audience just check with them if they know about this definition, because it's a diverse audience.
Okay.
It's a long thing, so if they're lost in the first lecture, there will be a problem.
Yeah, so feel free to ask questions anytime, okay? So if you feel that you need more explanation, I can do that.
I think some more explanation I need is that why such a margin always exists.
The margin might not exist. This is a classical case of separating hyperplanes. It's completely linearly separable data. But even if the margin doesn't exist, you can cut some slack and return a hyperplane. That hyperplane will also return these points as its output. So even if the margin doesn't exist, support vector machine algorithms return a hyperplane as in the form of the training data points.
I also don't have much idea about machine learning. So you said that those are training points, and so how is the machine actually getting trained? I don't know.
Okay. So this is not a machine learning lecture. So machines are trained. Think about solving an optimization problem. Think about there are 2 classes. You need to find a hyperplane which has a minimum norm, and such that these 2 classes are well separated. Think about from the line, and you solve this as a constant optimization problem. You solve it, you get the hyperplane.
So, in general, like, what is the size of the support vector in relation to the data set? If my data set is large, support vector would still be constant or something.
It could be constant. Yeah.
So, say what fraction is acceptable? I mean, it's fine if I really like some part of the support is constant, it's probably fine.
It's not fine. It might be someone's personal information. Right?
Okay.
Even releasing one data is not fine.
Okay, so the boundaries you should not even release one point of time.
Yeah. Yeah. It can be like that. This data point actually gives the equation. These data points gives the equation. No, so okay, that's a different question. Why it gives the data points? It's how it's designed actually. So another thing is if you just release couple of points. So now this computational thing comes up. If you just release couple of points, when you are doing the prediction, you use this returned points to do the prediction, and it will take a constant number of time.
So the questions don't get heard on this mic. So could you just repeat the questions online so we can
Okay, sorry.
specific this time?
So here the question was why support vector machine release data points, not a plane. So the answer will be computational, because if you release a constant number of points, then given a test point, you can compute the prediction and find the predicted level for a test feature. So that's why it releases the support vectors, which are training data points. So, but let's not digress here from the main topic. Let's not go to machine learning. Let's stick to differential privacy here, or privacy here. The bottom line is an output of a machine learning algorithm could reveal training data from a data set. Okay. So now consider the second example. So it's a chatbot, so based on GPT-2. So there are a lot of attacks that people have launched recently just by talking to the chatbot. So someone logged into the chatbot and typed this thing, right? It stouts about something, some garbage. And what the chatbot completed the sentence by showing this text, where you can see someone's phone number is there, some person's email is there, some person's name, as well as fax. So I have hidden this, but when the chatbot gives, it doesn't hide it. It just gives this, right? So, but just by writing some garbage, we can get some person's identifiable information like name, phone number, fax number, etc. So this is by doing adversarial prompting, we can make LLMs reveal sensitive information. However, I should mention that nowadays LLMs are getting trained better, and this kind of phenomena might not happen now. But when it first launched, there are a lot of things like that came up.
So how did they find this adversarial prompting, like with these talks were?
No idea. They do different kind of tokens. So there are different kind of tokens, like gave a poem and something came up. Yeah.
How did the LLM get this information? Is it
Yeah.
the same person's personal data or something?
It's a real data. It's a
Of
real
the
data
same
of a
person
person.
who is asking who
No. Some attacker or some adversary is trying to hack the system.
I think he's asking whose data is what he's asking.
Whose data is a think about your data, your name, your phone number, your email ID, and your employer information, everything.
LLMs has access to the other users that also have the account, and that
No, it's not like LLMs are trained on the complete web, like.
that
So the thing is, it has memorized that
This
text.
data was already public.
It could not be might not be public.
It's trained on the web, but
Yeah, maybe it has taken some documents from different organizations like that. Yeah. So why these kind of things happen? That modern ML models like LLMs almost memorize inputs. Think about another example is like autocomplete feature in Gmail, right? So since this modern models memorize inputs, so this kind of adversarial prompting can be done to make them reveal sensitive information. So these two examples show the two extremes of machine learning. One is support vector machine, where the output of the ML model itself reveals training data, and another is language models, where you can do adversarial prompting to get some sensitive information of a particular individual. Okay, so this is a data privacy problem in ML. There's a vast spectrum of this kind of attacks and this other kind of problems that data privacy problems that ML models have, but you can think about this as in two spectrum. Okay, let us now jot down what are the problems are. Okay, so given a database with sensitive information such as credit card numbers, your password of your account of some particular website that you are trying to log in with your account, we also sometimes say about passwords. So these passwords. So you are going to make some purchase. Sometimes in the website like Make My Trip, we say about credit card number. So information such as this, and also your name, age, bank details, biometrics. Like in other website, we also recently now say about biometrics. Similar, all these details we save right in some places of those websites. Also consider medical records, your political opinions, your religious beliefs. These two can be fetched from your social media activities, and medical records are in the hospitals. Hospitals publishes their annual statements where they need to record each patient's medical history and all. So given a database, consider a database which has all these informations. How can we ensure desirable uses of the data? How to use this database in a desirable manner to do some meaningful work, right? So you want to release some statistics from the database, how to meaningfully or desirably release the statistics while protecting the privacy of the data subjects. So these are all our personal data. How do we make desirable uses of the data while protecting our privacy? So this is the problem that we are going to tackle. Okay. So now let's talk about what are these different sensitive informations are. So this first example, credit card number, passwords are basically your credentials. Second are like your identification information, like your name, age. I think bank details should also go to credentials, but name, age, gender, and biometrics are your identification information. So your Aadhaar actually saves name, age, gender, and biometrics. So that is your identification. And your medical records, political opinions, religious beliefs, these are your sensitive information, right? Your political opinions are sensitive. If an adversary can harm you based on your political information, also religious beliefs. These are typically considered sensitive information, and for medical data, if you have a disease you do not want to reveal to anyone, that also considers as a sensitive information. All right. So how can we ensure desirable uses of the data? So what are the desirable uses? Like policy formation. Government are taking all this data and trying to formulate a policy based on our other data. So clinical trial, a drug company takes medical records from the hospitals and try to do some clinical trial on some new drug on a new disease. Sentiment analysis, like a lot of sentiment analysis are going on using our social media data. So all these kind of things comes in the field of desirable uses of the data. Like, and academic research is obviously one such desirable use of the data. Okay, and protecting privacy of the data subjects means we need to do this, perform all these tasks while making sure we hide individual information. So this will be the goal of the talk. All right. So what is the privacy in statistical databases? Okay. So there are individuals, data subjects, n number of individuals, their data are taken by an algorithm. Think about it, can be a machine learning algorithm, or it can be a person, it can be a statistician who is curating, trying to curate some statistics from the data set. Okay, so the data users like government researchers, companies, or an adversary. Maybe an adversary, maybe it might be me or you. So all these users have access to this algorithm in the form of queries. It doesn't get access to the data directly. It can access the algorithm in the form of queries and answers. Right? It can ask some query to the algorithm, and the algorithm is bound to give some answers to these data users. The answers could be, release some aggregate statistics of the data set, or release the output of the machine learning model that you have trained, right? Think about the support vector machine example, release the output, okay? So these kind of things are permitted. The data users can ask queries to the algorithm and get answers. It doesn't get the data. You have to see the data, right? So, and the goal will be to protect the privacy of the individual data users in this framework. So what are the plus points here? Why do we need to do statistical analysis? Because it benefits society. But the thing that we need to be careful about, that the statistical analysis is collecting large amount of personal information, so that this doesn't get breached, right? This personal information doesn't get leaked when we do this statistical analysis. This is the complete system of privacy in a statistical database. Any question here?
In the SVM case, can we modify the training data in such a way so that it's still classifiable but not invertible to the actual training
Yes.
data? And then
Yeah, that will be one algorithm to protect the privacy. Yes. You will not modify the training data, you will modify the algorithm itself. So that whatever the algorithm outputs, it doesn't output the exact data, it outputs some kind of perturbed version of it.
Sir, majorly when we use these algorithms, we just zero mean and divide it by variance for normalization. But is that normalization factor and that mean factor, it is generally not out in the public. So if it reveals also the support vector, how adversary is able to get it?
Adversary gets the vectors, that's the data points.
He can get the vectors, but those vectors are normalized. But he doesn't know what is the normalizing factor and the translation.
Yes.
So
But he can get the directions at least, right? Magnitudes might be different, but directions can be same. And if he has some, so we'll come to that. He might have also know this mean and standard deviation. So we need to protect against an adversary who knows that. We'll come to that. We'll assume that an adversary will know that's mean and standard deviation. We'll have to protect against that also. Okay. So as you see that there are two conflicting objectives. Okay, you have to do this statistical analysis that benefits society. Also you have to make the personal information protected, right? So these are two conflicting objectives. One is utility, how good your analysis is, and privacy, how private your analysis is, right? It's both of them hung in the balance. So utility means you need to release aggregate statistics which are of good use, and privacy is you need to hide individual information. So our goal will be to how to achieve utility while maintaining privacy. But before that, we first need to define what privacy is. That we have not done yet. So let's define that in the next couple of slides. And this lecture will define privacy, and we will give some foundation and analysis of these privacy definitions. All right, let's look at our first attempt at defining privacy. So data anonymization is the first attempt. So what it tells that remove obvious identifiers like your name, your Aadhaar number or social security number that uniquely identify an individual before publishing the data. before publishing a data, just remove these obvious identifiers, right? But will that work, right? If you remove all the identifiers from the data, right? That won't work because all the information gets hidden.
Sir, what do you mean by publishing the data? Like for us to give the data, that is what.
So suppose an organization requires to publish their data, right? So suppose a hospital requires to publish their patient's history. So before publishing, what they do, they encrypt everything or anonymize everything in the data, right? Right? So data anonymization tells remove only obvious identifiers like name, your gender, your social security number, etc. Not others which are not obvious, right? But suppose a case, if we remove everything, all the information, like or encrypt everything, it is not be of any use because data cannot be fully anonymized or encrypted and remain useful. So we will only remove the obvious identifiers, not other useful information in the data. Consider this example. It's a data set of n individuals, Alice, Bob, Charlie to Zora. The data set consists their postal code, their age, their sex, and sensitive information that whether they have some disease or not. The bit 1 represents that the person has the disease, and bit 0 represents the person doesn't have the disease. This is the data set, and we'll use this data set for the remainder of our today's talk as a a classical example. So now consider this person Zora. She has this disease. Okay. So how can we, if we use data anonymization, can we protect this information that Zora has this disease from getting revealed or not? That's the question we're trying to answer now. So first what we do, we take this and hide their names, right? Before publishing the data, we hide their name. Okay, so names are hidden. So we do not know now that Zora has the disease, right? Because names are hidden. So this data is now available to us. Do we know Zora has the disease? Okay, so looking at this, we do not know, right? Okay, or can we? So is there? Sorry? Postcode. Postcode can uniquely identify, but think of there will be multiple people with same postcode, right? Yeah, maybe, yeah, but there might be multiple people with having all of the same things, right?
You can improve your odds of testing.
Exactly, yeah.
You have reduced the probability, right?
True. Yeah, so you have really reduced the probability that okay, there might be 5%, right?
Yeah.
Okay, so you have reduced the probability. Okay. Any other suggestion? Okay, so we'll take this. Huh?
Other than anonymizing the name, we can also remove the last digit of postal code or something.
Exactly. Removing last digit of postal code.
Put some bucket in the age.
Okay.
This will also help in training the data, but creates a big range for it.
But that depends on the type of problem you're trying to solve. You can't be like, okay, just define a range.
Yes.
If you require a particular number, you should put it. You can't just remove it and then define an interval.
For some examples you can do.
Yeah.
So whatever you told that by doing all this, combining everything, we can reduce the zero in on the probability.
By symmetric encryption. So while training, we can map F and M to something else, and then after training is done, we can map them back to FMM, and where data is stored actually, FMM are not stored as FMM. We can have like some dark with some hash values.
But will that give us utility? That's the question we have to think about.
Since it's only encrypted during unencrypted during training process, so it's only unencrypted during working, and storage is encrypted. So like it's a real-time encryption.
Yes, it's a real-time encryption. It's another way. Yeah.
So the audience, online audience will not be able to hear the question.
Okay.
Repeat what
I see.
question.
The question is visible, right? How do we know now? Can we know that Zora has the disease or not? So yeah, so we have got couple of suggestions for the online audience that, so using all other information like age, sex and postal code, we can zero in on some person, right? Make the probability of that Zora has the disease more higher. We can also use, remove couple of the last digits of the postal code and put the ages in the bracket to make that, so that we cannot know that, yeah. And there is another suggestion, doing homomorphic encryption. Okay, so as we can see, all we'll see in the in the next couple of slides. All whatever you have said, all will be come to the play. So the question here we are asking is data anonymization safe or not, right? So whether anonymizing works or not. So here an example. So how can we breach the anonymization? So it's called linkage attack. Think about this dataset 1, which is an anonymized medical data. Okay, this dataset has several components like name, social security number, the diagnosis, which is you think about has disease or not. So it's a sensitive information. The visit date in the hospital, the medication that was given to the person, the information about the doctor. Also the dataset has the postal code, age and sex. Right? This is anonymized data because before publishing, what the hospital did, it cut out the name and the social security number. So obvious identifiers are cut out. So this is anonymized data. So our problem is to guess whether Zora has a disease, right, or not. So now take a dataset which is public. There are a lot of datasets which are publicly available. One dataset is public voter data. Our voter data are publicly available. It has name, social security number, date last voted, and date registered, and your address and your party affiliation, everything, right? It also have your postal code, your age and your sex. So these three, as you can see, are in the common. Now if we have this anonymized data and other public data where these three information like postal code, age and sex are common, we can use this public data to get information from the anonymized data. Okay, you can uniquely map it. And this is called re-identification by linkage. So uniquely link a record in the anonymized dataset to a record in a public dataset. And an estimated 87% of US population is uniquely determined by their age, sex and postal code. This study has found out that. And in fact, it has been this exact approach has been used to breach the privacy of the governor of the state of Massachusetts by Professor Latanya Sweeney in 2002. At that time, she was a PhD student when at MIT. When William Weld, the governor of Massachusetts, have announced that they have in his poll campaign, in his electoral campaign, he has announced that okay, we have a anonymized medical data, and they have released this data, and they told that this data is completely anonymized and your privacy is protected. Okay. Then Professor Sweeney launched this attack by using public voter data, and she actually got access to the governor William Well's medical history, but by launching this attack and send a physical mail to his house that she was able to identify his medical data by using this attack. This is called re-identification via linkage. Okay. All right. Now, what are these things, right? These are these crucial components: postal code, age, and sex, which are present in both the datasets, anonymized datasets as well as public datasets. These are called quasi-identifiers. It can help to identify person from an anonymized dataset. All right. Okay, now think about a linkage attack in practice. So Netflix has announced this challenge. I think in 2006 to 2009, they have announced this challenge. Okay, so they have a recommender systems. Netflix have their famed recommender systems, which they claim that okay, so they published the anonymized data of users, where users' name and everything was hidden, and some of the movie ratings of the users were that was presented in the dataset, and name and all the identifiers were hidden. Okay, so you can see, okay, some particular user have given thumbs up or thumbs down to some movies, right? And similarly, a lot of users are there, but their names and everything are hidden. So this data was published, and Netflix claimed, okay, this is an anonymized data, and announces a challenge. Challenge was to improve the Netflix recommender system, and price was this huge amount of sum. Okay, so it's $100,000, something like that. Okay, a team of researchers actually solved this problem, and were able to improve the Netflix recommender systems and took the prize. It happened around 2009. So how did they do it? Any idea? Do you know anything? Huh? Yes, like it's a matrix factorization technique they have used to solve this and improve the Netflix recommendation system. Yes, all those things will have been used. Okay, but now our problem is Netflix anonymized this dataset, and they published that, okay, this dataset is anonymized, so privacy is protected. But it turns out it was not. A linkage attack was launched by using public IMDb data. So you also go to the IMDb and you also read the movies, right? But this IMDb data is public. So this is an user Alice who has given this rating. Similarly, different users have given different ratings, but this IMDb data is incomplete. It's not that. So here, right, in Netflix have published this Alice's data, where for this particular movie Alice gave a thumbs down, but in IMDb data it was missing. But it is a public data. It knows that at least Alice have given thumbs up to this one and thumbs up to this one. So if you take anonymized Netflix data and public incomplete data, it turns out we can identify the Netflix data, right? Okay, so different users, by looking at these two puzzles, researchers were able to identify the Netflix data on average. So Narayan and Matikov in 2008 showed that on average, if we have 4 movies rating from a user, we can uniquely identify a particular user. It has been shown by Narayan and Matikov. And it reveals information as our movie watching history, which might be a public information which we do not want to reveal publicly. So our private information gets breached by this linkage attack. So what happened after they identified this Netflix data? That Netflix had to stop and had to issue a public apology. Okay, so the data was not anonymized. So it has been identified by this linkage attack.
On average, 4 movies uniquely identify a user. Can you clarify what this
Means that if you have ratings for 4 movies, both.
So it identifies users, those who have rated 4 movies on IMDb and Netflix
Together, yeah.
and that's all movies.
No, maybe or maybe not. But yes, it's a very unique kind of attack which I am not describing. But you can, I can give you a pointer. What is the exact attack is? But you see that the takeaway here is you only need a constant number of movies to identify user.
So this matrix columns you are saying is constant, or you are saying the number of entries in each row is constant?
Constant means?
So in this matrix, the rows are correspond to users and
Yes.
columns are correspond to movies.
Movies, yes.
So you're saying when you're saying average 4 movies, are you saying in a row only 4?
See, no, if I have 4 movies rating from a user, on average, if I have 4 movie ratings of a particular user, on average, we can identify.
I'm saying that in that case, in math term, it's
Yeah.
saying that in the matrix,
Call row.
for each row, if you have only like 4
Yes.
non-zero entries,
Yes.
you are able to recover.
Exactly. Yeah.
Sparse matrix, you are still.
It's a sparse. IMDb is a sparse matrix. Yes. Okay. So how do we know that if we cannot anonymize a data set because there can be linkage attack from public data set? Okay, now coming to this your solution of this, removing last digits of the postal code, or give the age brackets, right? This is called the second attempt. The exact solution was proposed by Professor Sweeney itself. That is called K anonymizer. So given a data set, so we have first figure out what are the identifiers. The name is an identifier. As we know, postal code, age and sex are quasi-identifiers which can be presented in multiple data sets. And your disease information is a sensitive attribute. Okay, and this information basically you want to protect. All right, now for this example, just assume that there are only 4% in the data set. All the other entries are not present. This is just for example. So what is first done? The identifiers were completely hidden. Okay, and in 2002, Professor Sweeney actually give a definition that, okay, so what we do, they suppress or generalize the attributes to make every record in the dataset indistinguishable from at least k-1 other records with respect to this kind of quasi-identifiers. See, right? So so every record should be indistinguishable from at least k-1 other records, right? You have to use only these quasi-identifiers to do that. So how to do that? Just remove the postal codes. Okay, so we see that 2% have same first 3 digits, right? So here k will be 2. So if I take this person's data, I cannot distinguish himself from this person because both have the same postal code, right? So k will be 2 in this example. Similarly for this 2, k will also be 2. You can also hide this age and sex information as of now and only focus on the postal code. So as we mentioned, we can make these 2 groups. This group of people have first 3 digits of postal code same, and this group of people have first 3 digits of postal code same. So we cannot uniquely identify any of them, any of a person from this group from the other, similarly for this group also. So this is called K anonymization. So now the question is, we cannot know that Zora has the disease, or can we, right? So because 2 persons have the same 3 postal codes and we know that this last one is Zora's data, can we guess whether Zora has the disease or not, right? Any guess?
Both of them have the disease.
Yes.
Put some probability measure on that.
No. So the answer is, you can see that both person in a group has the disease. So we know Zora's postal code. So if all person in a group has the disease, so the person has the disease. So the thing is, K anonymization also cannot work all the time, right? So if you happen to have this kind of groups, you might not be able to protect the sensitive information of Zora. Okay. So let's now look at another example of K anonymization. This picture is taken from this paper, and the method that I will describe is given in this paper. Ganta, Kashi Vishwanathan and Smith in 2008. So take these 2 tables, right? So, okay, think about 2 hospitals. Both of them are releasing K anonymous tables for patients' medical history. Can you tell what is K in the first table? What is K in the first table? 4, right? That means 5. K is 5 because k-1. You cannot. So K is 4. So if you take 1 person, you cannot identify 3 others, right, in the group. Similarly, in the second table, it's 6, right? So now, if we have these 2 K anonymous tables from same persons, right? They are same persons from 2 different hospitals. If each person can visit 2 different hospitals. So both the hospitals release these tables and all are K anonymized. Can we now breach privacy of some person?
The table 1 we can read the privacy of the
3.
All the cancer. No, like from 9 to 12.
All the cancer.
All
Yes.
of them have cancer. So if a person satisfies all those attributes, he
True.
must have the cancer.
Yes. Now think about that. The example where this kind of thing doesn't hold, right? Right? If someone who doesn't belong to this group, if he belongs to say this first group, and here also first group,
We can see that there's only one person who have AIDS in both of them.
yeah,
So we can maybe, and that's also less than 30, that's less than 35. So we can maybe do some analysis on both of them and then let's release some information about them. And similarly for, if we see there's no tuberculosis in here, but there's tuberculosis over there. And then,
but you cannot guess, right? 2 persons, you cannot guess from this group, right? But the first example that you told is correct. Say 28-year-old person visited both the hospitals. So now take this first data, less than 30, age is less than 30, has AIDS. Go to the second table, less than 35 has AIDS. So you know this person has AIDS. Just to take 2 tables into account and compose the information in these 2 tables. So if we do compose 2 tables, we can breach privacy. So when we define privacy, we have to take into account of composition also.
So we need to know that the same person has visited both.
Yeah, that we know. We need to know that a person has visited 2 hospitals. This auxiliary information we need to know. Okay? So we can breach that privacy.
Sir, in the hospital too, if like in less than 35 portion, if the viral infection was also there.
If
Now, like if below AIDS, instead of tuberculosis, if viral infection was there.
vital.
In the second row.
Okay. Yeah.
If viral infection was in the second row, then the thing is, it is matching with the first hospital also. So then we can't say for sure that the person is having AIDS.
No, we cannot first say this. No, this is greater than 35. We know this information. A 28-year-old person.
I'm saying now it is greater than 35. But if viral infection was in less than 35, in the table 2.
But it's greater than 35, right?
He's assuming a special.
Assuming, yeah.
But for this table, this is the case.
Yes, assuming in that case we cannot know. But the thing is, there is one example, right? One example of privacy breach. We need to protect that, even if it is a one example.
And one more thing, suppose this data is released and we want to use all these features for training a model. Now since we are removing some of the information, then like the task for the data scientist is also getting like complicated because he is having way lesser information than that is required.
Yes, that is the utility versus privacy trade-off. So how much utility should we sacrifice for achieving privacy? Okay, I think it's time for the first one.
Can break,
Yeah, break, right? This is the time or 10 minutes
yeah.
more?
I mean, now is the time, but whenever you
Okay, yeah, I think let's break here.
time to break. You have a 10-15 minute break. You can stay here, you can go out, take a walk. Up to you guys. Yeah.
But be back in 10 minutes.
Yeah, be back in roughly 10.
Over here, uh, we just showed that if we have released two data sets of same persons, same number, same individuals, using two different k anonymous conditions, you can still infer a sensitive information of a particular person. There is still a possibility to infer sensitive information of a particular person. So k anonymization doesn't work. So let's look at our third attempt. Instead of publishing these data sets, right, like anonymizing or k anonymizing, how about we release some aggregate statistics from the data set? Right? So the question that we are thinking, like, is granularity the problem, right? Releasing the data sets as it is, right, with anonymization and all, is granularity of the data sets are the problem or not? Maybe releasing aggregate statistics can help us. So what if we release some aggregate statistics about many individuals in the data sets? So let's look at this thing in more detail. Here is our data set, our favorite data set of Alice, Bob, Charlie, and a lot of other persons, and Zora. And say think about this data. So now think about this several persons are employed in a company, and this data set is with the health insurance provider of the particular company. So each employee they are all the employees of a company, and the health insurance provider of the company has this data set. It knows that it has disease or not because it is a health insurance company. Now the company, that the employer of all these persons, right, they do not know whether a particular person has disease or not, right? They know their postal code, age, and sex because they are the employees, but they do not know the persons have disease or not because it's a sensitive information. Now think about the company is not a good one, right? The employer wants to get some sensitive information about their employees, because if they figure out that some person has some disease, they can sack the person. Okay, so the company now can ask informations like the following, right? It can ask for information to the health insurance company. It can make this kind of queries. How many females have the disease, right? So now the answer will be, say, 2 or more, right, from this table, right? The health insurance provider will release these aggregate statistics, right? How many females have the disease? It will release this. That, okay, 2 or more. And how many, it can ask also some more involved questions like how many females living in a particular postal code have the disease, trying to get more closer to the answer. So the insurance company is bound to answer that also. Now think about the following question: how many females living in a postal code and aged year have the disease, right? Trying to getting to very close. And someone suggested that, trying to narrowing down the probability by asking different questions, right? So who suggested that? Someone from this place suggested that, narrowing down the probabilities. So this company is trying to do that, right? Trying to narrowing down the probability. Now, can the company now know that Zora has the disease, right? If the answer of this question is 1, it is, right? Because it knows the postal code, the age, right? And the female, the sex. So if the answer is 1, it knows the disease, right? But if not 1, if higher than 1, it might not. So the question we try to ask, whether releasing this kind of aggregate statistics of queries like this are safe to protect individual sensitive information or not.
If these questions overlap with each other, then we can narrow down the search and can locate the person.
True. So that's the problem composition. Multiple questions can narrow down the search further. So now, turns out that releasing this kind of aggregate statistics are not safe. So there are several kind of attacks which are launched to get sensitive information from this kind of dataset using queries like this. We'll talk about differencing attack. We'll talk about reconstruction attack, and we'll talk about membership inference attack. These three kind of attack we'll talk about. The focus of all the attacks will be to really get sensitive information by asking queries like this. Okay, so the company can make this kind of attacks. All right, let's go to the differencing attack. So this is our data set. The first four columns are known to the company: name, postal code, age, and sex. The sensitive bit is whether the person has the disease or not. It is not known, and it tries to infer that by asking questions like that. The company asks the following question: how many females living in this postal code 02120 and aged 40 have the disease? Right? Say the answer is 1, then it's very likely the company learned about Zora's disease, assuming that only one person has satisfied this criteria. Now we can make a counter argument. If the answer is 1, we are not aggregating anything. We are just answering a question. But our goal was to the health insurance company should release aggregate statistics. So it should not release these kind of answers because the answer is 1, because it's not aggregating anything. So this is not permitted, right? This kind of, so health insurance company should tell that, okay, I won't be able to answer your question because we're not aggregating anything, something like that. So if answer is 1, we're not aggregating anything. So a company will not know Zora's disease. But what if the answer is 5? Say a company has the same question and get the answer, health insurance company tells, okay, the answer is 5. The 5 females living in this pin code and age at 40 have the disease. So here, health insurance company has aggregated that information.
But there's another problem that depends on how many such individuals are there.
So 5, right? 5.
No, if we remove the health disease part, we just have how many females living in this postal district?
Yes, maybe 10.
Then the difference matters. Now, if there are exactly 5 and then they say 5 is same amount of information.
Yeah, but you do not know whether Zora is in the goal was to find Zora has the disease or not.
No, what I'm saying is, if there are 5 individuals with this exact, stats, not the disease stats, just these stats, and then there are the answer is also 5. Then also it's complete loss of information.
Yes,
Now
then it knows that everybody has it. That the group, K anonymous group that you have talked about before, right? The K anonymous group it founds. Using K anonymity, you can breach it. Everybody in the group has a disease.
The difference matters. If there are 50 people of that type and then they say 5, then it's less information.
Yes.
Okay.
True, you are right. Okay. So now think about the answer is 5. And there are multiple people, 50 people. So you do not know whether Zora has the disease or not. So now think about whether, suppose if the answer is 5, the company can still figure out whether Zora has the disease by asking these 2 questions. How many females living in the postcode and aged greater than or equal to 40 have the disease? It can ask this question. It can also ask another question. Living in 02120 and aged greater than or equal to 41 have the disease. So it is launching a differencing attack. There is a difference between the age greater than or equal to 40 and greater than or equal to 41. It is launching a differencing attack. The health insurance company will bound to answer these 2 questions. Say the answer to the first question is 4. Say 4 females living in this pin code and age greater than 40, greater than or equal to 40 has the disease. Answer to the second question is 5. 5 person whose age is greater than or equal to 41 have the disease, right? So now can you tell whether Zora has a disease or not, right? You can tell, right? If I think it's flipped, right? I flipped it. Yeah. Sorry, it flipped it. It has to be less than or equal to and less than or equal to 41. It should be, right? It should be flipped. Yeah. Sorry for this. Yeah, I flipped it. Yeah. So now you can do that, right? You can do in this less than or equal to 40 and less than 41. You can tell that okay, Zora has the disease. So now Zora's privacy is breached if she is the only 40-year-old female company living in this. But if there is more, it cannot be breached. But if this is the case, if she is the only 40-year-old living in this zip code and working for the company, and she is a female, and his privacy will be breached. So this attack is called differencing attack. Sorry to, yeah, for the mistake. All right.
Sir, like it is not mentioned that in 02120, whatever that postal code is, if she is not the 40 years old,
She is 40 years old. That knows. The company knows.
only, I am talking about only, like in that case answer was 5. But if that is not given,
Then it is not possible to breach it. I'm just giving a couple of examples that launching this kind of attacks,
in a very specific case which is practically not
the
time.
practically it is possible, right? There might be only one female living in a postcode with age 40 working in a company, right? This is a practical example, right? A person living in an area, age 40, working in a particular company. This is more or less a practical example. So, okay. Now let's see the reconstruction. How can we reconstruct people's data from these statistical tables? So we have talked about differencing attack. Let's go into reconstruction attacks. Okay, so if you see that we have asked questions of a specific form, right? How many people living in a postcode have age have this disease or not? So is our specific questions the problem or not, right? What if instead of asking specific questions, we ask only some benign kind of information which does not reveal this kind of specific information? Can we protect the privacy for that case or not, right?
How do we define benign in this?
Yeah, think about not very harmful kind of, like not very specific thing. So take this table. This is a table released by US Census Bureau. So it's a statistical table. You can see a lot of statistics: total population, number of females, number of male, the number of what is the count of total population. These are good of a particular postcode or particular block of a neighborhood. You can see their age, median age, mean age, and this is a table, right? The different black or African Americans. Right? This is a table that has been released by US Census Bureau every year. So census releases these statistics. So what can we infer? What can we learn from this table? Right? Can we learn anything? Okay, now think about there are some entries which is marked as D. D actually basically tells that, okay, if count is 1, then it is not released. It has been not released. That's what we discussed, right? We can only release aggregate statistics. If there is nothing to aggregate, we won't release. So it just tells that, okay, just releases D.
So the single person is female, so the other 3 people are married.
Yeah, so you're going right direction, but yeah. So you can infer a lot of information,
Even
right?
with the black male, we
Yeah.
see one black male, there are black African female, 3 black African is 4. So there has to be male to be 1.
So all of you are doing are like everyone can do this, right? So a lot of information can be got from here. So let's look at this particular statistics. Number of males, median age is 30 and mean is 44. What can we learn from these statistics? So we have this prior knowledge. There are 3 male persons, M1, M2, M3. Their age can be higher, greater than or equal to 1, or less than or equal to 125, right? And you might ask why 125? So highest known person alive was not alive. There was the highest age the person was lived was 122. Then we are assuming, okay, say 125 can be the highest age. Seeing at the table, we can know that, right? This is a prior information. We do not need to see at the table. So how many possible choices for M1, M2, M3? If we do this permutation combination, we can find there are 341,376 possible choices of M1, M2, M3 that satisfies this condition. All right, now we have this table where we have median age and mean age. What kind of information that we get from this table? So from table we see that M2 is 30. Second person's age is 30. Here we are assuming that M1 is less than M2 and less than M3. So why M2 is 30? Median. So 3 persons, M1 is less than M2, M2 is less than M3, so M2 is 30. Median gives us that. The mean will give us M1 plus M2 plus M3 is 132. 44 into 3. Okay. So the subtract M2, we get M1 plus M3 is 102. So now we have all this information. Now it turns out it boils down to 30 choices only. You can have only 30 choices of M1 into M3. So seeing this benign looking table, you can get you can reduce the uncertainty from this big number to only 30 choices. And in fact, you can tabulate this. You can write, tabulate this in a table. These are all possible 30 choices. So see how much information we can infer, right? So this is like, even if we ask for some benign information, give the mean age or median age, if conditions in our favor or in condition in adversary's favor, he or she can do a lot of inference from the data set. So already reveals a lot of information, right? So this example tells that reconstruction from statistical table is possible. Any question?
Can get even more data.
Yeah. More is possible. Let's just use an example. Yes.
Because all of these examples, the counts are the problem. What if before releasing the data, we modify this table in such a way that instead of having one Zora, for example, we'll have multiple similar looking Zoras, so that that won't, and that's for odd people, so the mean and median remains the same, but instead now it's very hard to sort of narrow down, because now we have a bunch of.
But you cannot reveal the information which it doesn't have, right? Census cannot reveal this kind of information. If there is only one Zora, you cannot reveal multiple Zoras.
Census can't do that. But if I releasing some other data for public use, training or hospital data.
But if that data is junk, whatever statistics you release from that data will not be good. That is also one of our goal, right? We need to do some desirable things or useful things from the statistics.
But if we are only releasing the mean and median type of things, then it shouldn't matter, right? If I scale the data without.
Okay, so you are taking that you would do some junk and release median, mean and median. True. That is one approach. In fact, we will see that it will be related to differential privacy. Okay, this attack on statistical disclosure methods was used was given in this paper, Garfinkel et al. In 2019. They have launched this attack on that US Census Bureau. Alright, let me now describe a reconstruction attack. We go to our favorite dataset, n individuals, identifiers. So these four now I'm now clubbing both identifier and quasi-identifier together and calling them identifiers, and denoted identifiers by Z. And the sensitive information I'm calling secrets and denoting secrets as S. And there are n number of individuals. And our goal will be to infer Zora's sensitive information. Right? Think about it. So what are the identifiers for Zora? Is name, postal code, age, and sex. And the secrets of Zora is 1. Right? So Zora is nth individual, so all are subscripted by n. Let us recap. We're asking queries of the form: how many individuals or females older than 40 have the disease? This kind of queries we were asking before, right? And what we want to release, right? When we ask queries like that, what do we want to release? We want to release some count statistics, right? How many individuals older than 40 have the disease? So you release count statistics of the form this: sum over j equal to 1 to n. Phi is a function which takes the one identifier, jth person's identifier, and maps it to a Boolean value, 0 or 1. S is the secret bit of that particular jth person. So sum over all this will have this answer, right? So we want to release count statistics of this form. So phi I call this a query condition. Condition of a query. It can be 0 or 1, right? So can you guess, for this question, what is phi of zi for a given individual? For this question, what is phi of zi? So if I take a person, say Zora, what will be phi of zi? It can be 0 or 1 only. For a particular individual, it can be 0 or 1. So you now take Zora, what is phi of z? Older means, yeah, take greater than or equal to 1, right? So because it's older than 1, so phi will be, phi of zeta will be 1. So it will, so query conditions will be like that. It will just check for each individual it is greater than or age is greater than or equal to 1 or not, and return 1 if it is, and 0 if it is not. So phi will be like that, and Sj is your disease. So if you sum it up, you will get how many individuals older or greater than or equal to age 40 have the disease. So these statistics are like count statistics. So now I introduce vector notation, a vector phi of n length, phi of z1 to phi of zn, and a vector of secrets s1 to sn, and take a dot product. You know dot product, entry wise product, and sum it up. So this is equal to this. So what is this vector? These 5 vectors. I call this vector as f. F is a vector of n length of Boolean entries. Each entry can be either 0 or 1. That is f. And I call this vector as s. The secrets vector, as s also belongs to 0, 1, and it's an n length vector. So I take two this vector f and s and take their dot product. I get the count statistics. So count statistics will be like take the, and f is now the f is similar to the query condition, right? F specifies the query condition. So I'll denote f as the query from now on, and s are the secret bits. Given a query f, which takes from 0 to 1 to n, and a vector of secrets s, what is the count statistics, which is the dot product of f and s.
So do we try to do the span of it or something and try to like keep the restriction?
Nothing, just doing this, no span, nothing. Tying this simple things. Okay, now what is a reconstruction attack? So in launch, this is a notation, and we launch this following attack. We'll ask k queries. We can ask multiple queries of this kind of form, right? So we ask k queries input. Each query is given by a vector f1 to fk. All are n length Boolean vectors, and we get k answers a1 to ak. Right? What could be the answers of this kind of count statistics values, right? Or some kind of, some values with some errors, right? Whenever the value answers are reported, it might have some errors, right? So let's denote answers as a1 to ak. Obviously, it's a statistics, so it will be a number in the real line, right? So that is the input to the attack algorithm: k query vectors and k answers. And the output of the attack algorithm will be to output a vector of secret s tilde, which is different than obviously s. This is the output of the algorithm. This is a vector of secrets of n length vector of Boolean values that minimizes the following this quantity, which minimizes the maximum error, right? S tilde. So if you, this is fi dot s tilde is the reported count statistics, right? The predicted count statistics. If you output s tilde, the predicted count statistics will be fi dot s tilde for ith query. AI is the reported count statistics. Take the difference of these two. This is the predicted value and this is the reported value. Take an it's a mod of that and do it for all the queries. Find the vector of secrets s tilde that minimizes the maximum of all the errors. Okay, this is the simple algorithm.
Wouldn't this be predisposed to let everyone after certain index have no disease because of how we are grading? Wouldn't this have a tendency to sort of guess that no one has a disease because that have a smaller norm than telling that it will have a disease, right?
No, we are not trying to do anything like that. So your question is, what norm is this?
We're trying to reconstruct the data set. It would predict that after a certain point everyone won't have the disease, right? When we're trying to
After certain point means what?
number of indices.
Number of?
Suppose the data set is n columns long or n rows long, and if you're using only k, from k plus 1 to n.
No, k is queries. K is not on the dataset size. K is some number of queries.
K is queries, and we are querying, let's say 1, 2, 3, 4.
No, it's not like that. We are doing aggregate statistics. The queries are not for a particular person. Queries for over the entire dataset.
Okay.
over the entire data set. Like how many individuals in the entire data set older than 40 have the disease. So we have queries of the form.
Is it the idea that there are multiple vectors of sequence which minimize this? So if the minimum is not unique,
Minimum will not be unique, that we need to think about that. But even if minimum is not unique, I think we can report one. I'll get back to this question. Right? I've not thought about this.
Sir, is there a lower or upper bound on the value of k?
No, there is no lower or upper bound. There will be a lower or upper bound that will come when we do the proof.
Like
Yeah.
the features these identifiers have very high variance, then in that case you won't be able to get
Yeah,
close
true,
that
true.
minimum.
Yeah, we should assume that the number of the answers that are being reported should not be too far from the true answers. That we need to assume. Otherwise, the attack won't be successful. Right? That's your question. Right? That will be the upper bound on A. Also a lower bound on A. Does this answer your question?
My question was that if these identifiers, these have very high variance, then we need a lot more number of questions to solve this problem.
True. Yes, we'll see that. We'll need a lot more number of questions. We'll see all this.
So is there a metric by which we can approximate like how many new questions we should ask based on what kind of attention?
Exactly. We'll see all this. So the question was, what is the number of k, right? How many queries we need, right? So we'll see all this in the next couple of slides. And another question was about the range, right? How big the values will be A1 to AK. So to make the attack successful, the answer should not be junk. Answer should be close to the true values, but it will allow certain amount of noise, a certain amount of errors. So the answer, the attack is clear to everyone, right? This is the attack. This attack is launched on this data set. Okay, so here I have written down the attack again. So the hypothesis, now coming to your question. Each query is answered within an error alpha times n, where alpha is a number less than 1. Okay, that is S is your true secret bit, true secret vector. Fi is ith query. If I take dot product between fi dot s, this is the true count statistics for query I. And ai is the reported count statistics for that, right? So difference between fi dot s and ai, the true count statistics and the reported count statistics should not be larger than alpha times n, where n is the number of data points. This is the hypothesis, this we assume. Maximum error is permissible for all the queries is less than or equal to alpha times n. But alpha is as of now, think about alpha is a number less than 1. Okay, this is the hypothesis that the range of ai will be fi dot s plus minus alpha n. Okay, so if this hypothesis is true, then the attack, what is the success probability or what is the success rate of this attack? Then the reconstruction error of this attack, so that means s tilde, that means what is the reconstruction error, which is fi dot s tilde minus ai minus fi dot s. Fi dot s is the true count statistics, fi dot s tilde is the reported count statistics. This is the reconstruction error of this attack. We can show that reconstruction error is at most 4 times alpha n. If the attacker makes k equal to 2 to the power n queries. This answers your question, how many queries are needed, right?
2 to the power n is not practically feasible, right? Like,
Yes.
all the data points are here, you need 2 to the power 1000 queries.
True.
I'm not gonna do that. Right?
Yeah. So this is that, right? You need to have some number of queries. So k into 2 to the n queries are needed to get the error less than or equal to 4 times alpha, right? So this answers your question about how many number of queries are needed. I will come to your question later. So the question is, this is not a feasible, right? 2 to the n is not a feasible number because n could be very large, and it's a correct question, and we'll come to that. Okay, so this is, I am not giving the proof, but it's very simple. I think some algebraic manipulation you can get that. So this is reconstruction error. What is number of entries where the vectors s and s tilde differ, right? So what I told, reconstruction error is difference between fi dot s and fi dot s tilde. Since all are Boolean random Boolean vectors, it's basically nothing but number of entries where s and s tilde differs. This is the reconstruction error. And then we are doing k equal to 2 to the power n queries. That means we are using all possible queries that we can make on this data set. In n number of data sets, we are making Boolean queries. We are using all possible queries. Obviously, it is not practically possible. But however, the attack is very good, right? Think about alpha equal to 1 by 100, right? Then, so it will be 4n by 100. For n data points, the error will be 4n by 100. So 96% of the bits will be recovered with 1% error only, right? Think alpha equal to 1 by 100, just put it here and divide alpha n by n. So the relative error is 1 by 100. So if the hypothesis is telling that if we have only 1% error for all the queries, right, then this attack will recover 96% of the secret bits. So there are n number of people or 100 people, so 96 people's secret bits will be completely recovered by this attack if we are allowed to make 2 to the power n queries. Okay, so quite powerful attack. But the question is whether this attack is realistic or not, right? No, because as we have already answered, it's because 2 to the power n queries, it's exponential in the size of the dataset. Think about n equal to 100, it blows up. So what should we do if number of queries are very, very less than 2 to the power n? Right? That's the question we should answer now. Any question now? Yes. Yeah, not insurance company, the employer. Employer asked to the insurance company how many persons aged 40 has the disease. It should not give the exact answer. It will give the answer with some error. And if the error is very less, right, 1%, like out of 100 individuals, only 1% data it just tinkers with when releasing the aggregate statistics. Error is very less. Still, with this attack, the employer can recover 96% of the disease information of their employees. This is what the attack and this result tells. Okay, but now we try to see how can we launch an attack when the number of queries are small and less than 2 to the power, at least not exponentially large. All right. Yes.
So when you say 96% is recovered correctly, so if I understand correctly, like we know that on an aggregate 96% of the bits match, right? But we don't know which 96%.
Yeah. We don't know which.
Recovery useful then in that case. Is it a good definition of recovery?
Yeah, it's true, right? It's whether it's a good definition or not, right? But it's an attack that aggregate statistics also can reveal a lot of aggregate information of the data. But with some particular, when it will be useful if the adversary has some auxiliary knowledge which he can fall back on, right? So ultimately the definition that we will want to come up with for differential privacy, which will need to account this kind of 96% of error revelation as well as any auxiliary knowledge which can help this. Alright, so we need to now launch an attack where it is practically possible. So we have same hypothesis, each query is answered with an error alpha n. Then suppose we make k equal to order of n, linear number of queries. But how we choose these queries uniformly at random from the set of all possible 2 to the power n queries. There are 2 to the power n all possible queries. I pick each query uniformly at random from that set. So I pick n such queries. Then we can show and launch the same attack. This k query will be order of n, and how do the adversary or attacker will select the query? It will be taking this k query vectors which are sampled uniformly at random from this all possible 2 to the power n vectors. This is how the query vectors will be selected, and the query vectors will be passed to the health insurer, and it will answer k answers with this only this much amount of error. That the error should be bounded by alpha times n for each query, each of these random queries. And now this is the proposition, and the adversary will launch the same attack. Output a vector of secret S tilde that minimizes the maximum possible reconstruction, maximum possible error between the predicted counts and the reported counts. Same attack, but only thing it is changing a linear number of queries, and that the queries are chosen uniformly at random from all the 2 to the n possible queries. Then we can show that the reconstruction error, which is what is reconstruction error? If you remember, number of bits where S and S tilde differs, that is the reconstruction error. The reconstruction error is at most order of alpha square times n square with probability, very high probability, 1 minus greater than 2 to the power minus n. If n is large, this 2 to the power minus n is very small, so 1 minus 2 to the power minus n is very large. So very high probability, the error is now order of alpha square times n square. But we only need order of n queries. The cavity is we need random queries, need to select random queries. So randomization is helping the attacker. Okay, any question now? Okay, so powerful attack. It is also a powerful attack. We can recover nearly all the secret bits from answers with error square root n. So if the error here is is much lesser than square root n, right? The alpha n, this quantity is much lesser than square root n. When will that happen? Think about alpha is much less than 1 by square root n. So alpha times n will be much lesser than square root n, right? Then what is the error? If alpha is much less than 1 by square root n, if I put alpha here, right? Okay, so it will recover nearly all the secret bits on average, right? Okay, so now think about whether this attack is computationally feasible or not, right? Why? Because when we are doing this maximum over I equal to 1 to k, right? We're still searching over the all possible square space. We're still searching for a secret vector S tilde, which is a Boolean vector of n length of entries 0 or 1. That means 2 to the power n number of choices. From 2 to the power n number of choices, we're still searching from this vector S tilde. So it's still a computationally hard problem because the search part is computationally hard, right?
You can employ some search algorithms like optimization algorithms, because at the end it's just the optimization problem. You need to find S such that the function is maximized. So we can apply some optimization algorithms to more efficiently search the space.
Okay, someone has suggested that we can do optimization algorithms over the space to more efficiently search that, right? Any idea what can be the optimization algorithm?
Not sure, but I think some linear programming or something like that would help, because the space itself is linear.
Yeah, so we'll see that exactly this is the answer. In the next slide, we'll see that we can do solve a linear optimization algorithm to tone down the complexity from order of 2 to the power n to order of n. Yeah, so as we mentioned, attack is not feasible because there are 2 to the power n possible vectors and it's not computationally feasible, right? So how can we make the attack run in time polynomial in n? So there, now we'll see this. Okay, so now it's a reconstruction attack, but it's a compute friendly reconstruction attack. Same attack, okay, same attack is not changing. Think about the same attack. Oh, sorry. Yeah, so we cannot do this, right? Because it asks us to search over 2 to the power n choices. So we cannot do this. So this is out of the question. Instead, what we do, we launch a different attack. We output a vector of secret S hat, which is not a Boolean vector, but it is a real vector in n dimension. The dimension of both the vectors are same, but instead of a Boolean vector, it's a real vector. That will minimize the same error, right? So fi dot sat is the predicted counts statistics and AI is your reported count statistics. So this is the difference between these two count statistics. Takes a maximum over all possible queries. So it's a maximum error difference between the reported and predicted count statistics. So S hat is the vector which minimizes this maximum error. So we get a vector S hat which is in real, but we need to output a vector of secrets which is in the booleans, right? So what is the easy way to do that? Just round it off. Get a vector of reals and just round it up to 0 to 1, right? So take some threshold and round it off, 0 and 1. Okay, so this is the attack now, which is, so it will be compute friendly because we're solving a linear programming problem. It's a linear programming problem. So this is a compute friendly. So now what are the rates? So think about, so we are now considering alpha is less than 1 by square root n. So the error is much lesser than square root n, right? This is the hypothesis that all the queries are answered with error much lesser than square root n, right? Then the same results, I'm using the same results from the previous slide. Also the results do change a bit, but for the sake of brevity or simplicity, I'm quoting the same results, which doesn't alter the high level idea of the result. The result is that nearly all the secret bits will be recovered with very high probability if the attacker makes a linear number of queries chosen uniformly at random from these 2 to the n possible queries. So same result. It will be all the secret bits will be recovered with a very high probability if the error is much less than square root n. And we have n number of queries. So now this attack, which solves this linear programming problem, it is polynomial in the dataset size. Because it's a linear programming with n variables, so S hat is a vector of n dimension. So it's n variables. So if you were not familiar with linear programming, you can think that you are basically trying to find a solution to optimization problem where the variable that you want to learn has n components. It's a vector you want to learn which has n components. So the number of variables which we want to learn is n, and number of constraints. That means you want to minimize an objective as well as you have to satisfy some constraints, right? Some feasibility constraints. So here since there are only k queries, number of constraints will be k, right? For all queries we have to satisfy this, right? So number of queries will be k. So the number of constraints will be k, and we have assumed that we'll only draw order of n number of queries, right? So it's a linear programming problem in n variables and k equal to order of n constraints. And the rounding, we're also doing a rounding off, right? We're taking this real vector and rounding off to 0 to 1, right? This is also, we're going to each entry of the vector and rounding it off, right? We're doing it n times. So the complexity is also linear. So linear programming in n variables, the complexity is order of n log k. So you can think about it's a linear kind of complexity is linear in number of data points, data size. Huh? Yes. Yes. Next slide. Yeah, I'm just putting out the values of the errors, values of the alpha. Yes, number of queries, I'm keeping it fixed. Number of queries, I'm keeping it fixed. So here there is a typing mistake here. So it's not a reconstruction error, sorry. It's a typing mistake here. So it's a reconstruction accuracy. It's a typo. So reconstruction accuracy will be this. So, okay. That means this number of bits will be actually recovered. So it's a typo. Sorry for that. So your question was, this slide it is alpha times n, right? Next slide it is square root n, right? Alpha, right? So what I am doing, I am just putting alpha is much less than 1 by square root n. Right? If alpha is much less than 1 by square root n, then the error is much less than square root n. I'm just using for the, in the next slide. So for this slide purpose, think about alpha is much less than 1 by square root n.
So the difference in time complexity is mainly because that here we are solving the optimization problem by searching for all vectors, but there we are just like we are rounding it off.
There, yes, the question was about whether what is the difference in the time complexity. So here we are doing a optimization over these 2 to the power n possible choices, right? There we are solving a linear programming with n variables. So your question is answered, this alpha thing. Is it time or let me finish this reconstruction attack, right? Okay, so the thing now we have a attack which takes only linear number of queries, which succeeds very high probability, that in the sense that nearly all the secret bits. How? Let me just go back and tell you. So here this is a typo, it should be reconstruction accuracy. That means how many bits are recovered. So think about it is order of alpha squared n squared, right? And put alpha equal to 1 by square root n, right? Then it actually goes down to order of n. That means nearly all the bits are recovered. Okay. So we have an attack now which takes only linear number of queries. It is very successful with high probability, and it also runs polynomial in number of the data points. So we have a perfect attack now. So, but there is still a cavity. This reconstruction attack only work when this error is much less than square root n, right? We have put alpha is much less than 1 by square root n. So reconstruction attack is working only if this error is very small, right? So there is still a cavity, right? So what happens if we allow an error is greater than square root n, right? This is if the health insurance company answers the queries with much error, larger error than square root n, what happens? Is there any attack which can breach that also, right? So that we'll see next. These are called membership inference attacks. So I think I'll stop here for the next one.
Coffee, 20 minutes break. Should have coffee.
Yeah. Okay.
Can we get these slides?
Yeah, I will do it. I'll share it. After all the lectures are done, I'll share with it. I have to make some modifications.
Yeah, because noting down all these points out.
True. Slides, you will get it.
Send it to me, I'll upload
Yeah,
it.
yeah. Thank you.
How can the reconstruction accuracy be alpha square n square? When alpha
Discussed about using linear programming to better down the region. So, is this a convex optimization? How can we?
It's a convex principle.
Why is this a convex optimization?
It's linear. It's a completely linear programming. Linear functions are complex functions. It's better than convex. It is linear. You can just solve it in linear fashion. What to start? Okay, I think it's a long day for you guys, right? From morning. Let me bore you guys for 45 minutes more. Right? So what we have seen a reconstruction attack, which is compute friendly. It takes only linear queries. Reconstruction attack, which is compute friendly, takes only linear queries chosen random, and can recover nearly all the secret bits with high probability. Right? So it's a compute friendly as well as doesn't require too many queries. All right. So now we have discussed. So, but it works only when the error is much less than square root n, and if the error is greater than or equal to square root n, then reconstruction attack won't work. And so we need to have some different attacks. So as I mentioned, membership inference is another kind of attack, which will work when allow is greater than square root n. But before going to membership inference attack, let me tell you a practical example of the reconstruction attack. So it's a reconstruction attack in practice. So the challenge is called Defix challenge. So Defix is a company, or it's a system. Defix is a system developed by a startup which releases or which computes statistics from a private database, from a database where there are sensitive informations. So that's what the system does. It should release statistics from a private database. That means it should not release statistics as it is. It should release a noisy version of the statistics, right? It should release statistics with some error. And how do it it does that? It can make SQL queries on a database while preventing disclosure about the individuals. Only by making SQL queries you can release the statistics, but you also need to make sure the individuals information cannot be disclosed, right? So that's what Defix does. So here is an example of a query. So think about a lot of people have applied for loans, right? A lot of individuals have applied for loans from a bank. The bank maintains all the ledgers, right? So individuals and their names, address, their occupation, and whether a loan was granted to the individual or not, right? So this loan is a secret information, because if your loan is not granted, then people might infer that your income is not good enough, right? You have some issue in your credit history. So loan is a secret information, and Defix can do this kind of queries, SQL queries, select count from loans. Loans is a data set. While loan status is C, that means loan has been approved. and client ID between 2000 to 3000. That means clients are given some IDs in the system. So this kind of queries, SQL queries you can make, right? SQL queries. So these loans are secrets, and this client ID, as you can see, these are identifiers, right? It identify each client. Now, there's a question: can the system provide exact counts, right? So no, because if the system provides exact count, what will happen, right? You can do differencing attack, right? That we have mentioned before, right? You can ask between 2000 to 3000 and between 2000 to 3001, something like that. You can ask these kind of differencing attacks to breach this system. So it cannot provide exact counts because its goal is to prevent disclosure about the individuals. So what it does, it add noise to the counts. So that's why it will always add noise to the counts. It will not reveal any exact answer. It will always add the noise. Now, what about reconstruction attacks, right? Differencing attacks cannot be done.
So is the noise have a distribution or it's a fixed noise?
It's a distribution.
So like if you run this query again and again, we can make a noise plot and then do some.
Yeah, noise can be distribution. Yeah. It's not random. It's not fixed.
Yeah, so like then you can just query this thing same again and again. It will give some different answer.
But then you can also plot it and find out the distribution of
Get
it.
some inference from it.
That's right. So how much noise is the good one, right? That is the question. You're thinking in the right direction. How much noise is the good one? Alright, so defix will add some random noise to the counts. So now think about efficient reconstruction that we have mentioned, right? Which runs in a linear time. It only requires random queries, right? You have to select n queries from 2 to the power n choices. Recall that, right? We have discussed that. So if you do some kind of random queries, the reconstruction attack succeeds, right? So what can be a random looking query, right? This is an example of random query. Select count from loans where the loan status is yes, and client ID between this 2007 or 2018. That means you can randomly select some clients, right? Randomly select some clients and put it. So this is some kind of random query, right? This random query you make it, right? Now we know. Now, yeah, the thing is, defix knew about this. Defix know this. If you do random queries, order of n random queries, and if the error is less, right, then reconstruction attack is possible. So an adversary can do a reconstruction attack and get the loan status. So it needs to prevent from this kind of reconstruction attack also, right? This kind of queries, which are random queries. So defix knew about this, so it needs to add more noise, right? Okay. So the thing is, so that's why what they designed a rule that if an attacker asks this kind of queries will be answered with greater than square root k error. So if number of terms in the query, this number of client IDs, right? If number of client ID, this is the number of terms, right? In the query is k, right? Think about it. Then it will be answered with greater than square root k error. Why? Because if the terms are randomly selected, right? So you are selecting k from n number of client IDs, right? If these are randomly selected, then k would be order of n, right? So whatever k will select, it will be around the order of n because these are randomly selected. And then defix will answer with greater than square root n error. So since k is order of n and defix have post this rule, queries of this form will be answered with greater than square root k error. So it will answer the query with greater than square root n error, around that sort, right? And it knows, because it knows that reconstruction error needed much less than square root n error to succeed. Since it knows that, it designed everything like that. So far so good. Defix thinks that if I do like this, there will be no reconstruction possible. The error will be greater than square root n. Random, even if people do random queries, in linear number of random queries, reconstruction error won't be possible. So it designed the system like that. Okay. So, but the thing is, this system can also be breached. Cohen and Nishim in 2018 showed that you can make some random looking queries like this, which are not random but random looking queries, but random enough queries, but not completely random. And you can breach this diffuser system. So their query is like this: select count from loans such that some condition is satisfied. This condition is floor of 100 into client 2 into client ID to the power 0.7 is equal to floor of this plus 0.5. This kind of queries they have done. And client ID between 2000 to 300. That means take all the client IDs between 2000 to 300 and 3000 and check for those client IDs. Return count of those client IDs which satisfy this condition. This is not a completely random. You are not selecting client IDs randomly from the numbers, but you are putting this condition. It's not completely random, but it looks like random. So random enough. So this kind of random enough query they have launched. But the thing is a random enough query. But number of terms, see the number of terms, right? Here the number of terms will be k, right? Client ID 2007 or client ID 2018 or client ID 2019 991. K number of queries. But here the number of terms, this is constant. So you can make constant number of queries, which is random enough. But and what is the defix rule? It will tell that if number of terms in the query is k, I will answer it with the error greater than equal to square root k. So this query, number of terms is constant, so and the error will be constant. It will release the answer with some constant error. Okay. So the error doesn't scale with square root n. Right? So error will be much less than square root n. So reconstruction attack will be possible here. So by launching this kind of query, in this paper they have made sure defixer system can be breached. Okay. Full victim, it fell full victim to reconstruction. And then what defix do? Defix acknowledge there is a problem in their system. They incorporated these things now. Now every year they launch this kind of different challenges and give some prize money. I think I think every year it's going on. And their goal is if someone can breach their system, get the prize money, and they will implement that to improve their system. This is how they are now operating. This is a practical example how reconstruction happened in practice. So I have not given the reconstruction how reconstruction example, just gave the attack, but you can get the full picture. Right? So in reconstruction attacks are very much possible in practice. All right, and let's go to our next topic, membership inference attack. So we have our favorite data set, Alice, Bob, Charlie and Zora, n individuals. Okay. Now think about how this data set is collected. Think about there is a distribution of this population distribution, a distribution of lot of people, right? So think about a lot of people in an area and what kind of, and how many people are there, what are their postal code, and all the people are there in a big distribution, and you are sampling from this distribution to compute this, to come up with this data set. You are not taking all the persons from that population, you are sampling some populations randomly and coming up with this data set of n persons. Okay. Now an algorithm, it can be a machine learning algorithm or some statistical query algorithm. It has this data set. It takes this data set as their input, and there is also an adversary who can communicate with this algorithm. Remember our when we told that how this statistical database privacy is think about. Adversary can communicate with the algorithm, but by making a query to it, and algorithm will respond by giving some aggregate statistics about the database. Adversary doesn't know about the data set, right? Adversary wants to infer Zora's information, but it can only do by making some query to the algorithm and getting some aggregate statistics which can be noisy from the algorithm. Right? This is the entire framework. Now Zora is the target person. Adversary wants to get Zora's data. So membership information attack tells that, okay, we'll give adversary Zora's data completely. We'll tell her, okay, this is Zora's data. So adversary's goal, so adversary gets Zora's data, okay? And how so adversaries get Zora's data, and now we'll tell adversary the following. The Zora's data are either chosen uniformly from this data set, so there are n number of persons, either uniformly sampled from this data set, or this data is drawn independently from the distribution itself. So think about now from the top, from the distribution there are a lot of people. So this data set was formed by sampling n people from the distribution. And adversary is given a target individual data. And it has been told that this data is either chosen from this data set, independently from across all these rows, or it has been drawn independently from the population distribution. This information has been given to them. It is not, adversary doesn't know whether this data belongs to the data set or not. This the adversary doesn't know, right? Data, we know that data belongs to this database, but the adversary doesn't know. It only knows it is either coming from the database or coming from the population.
The adversary knows the secret.
Everything, either full data, but it knows either from this, it is coming from the database or it's coming from the population distribution, right? And its goal is to predict whether Zora's data was in the data set or not, right? In or out. Out means it was not in the data set, in means it was in the data set. That is its goal, to predict, given a target point, to predict whether it was in the data set or not. That means whether the algorithm used this data as its training point or not. So that's what the goal of the membership attack is. So it will be given the data, but it needs to predict whether the algorithm used that data or not. And there is some auxiliary information that adversary has. Adversary has some knowledge about this population distribution also. Some knowledge about this population distribution. That also some extra information adversary has. This is the entire framework. Any question about this framework? Okay. Okay, yeah. Yeah, so here is the summary. Attacker gets access to algorithms output, access to individuals' data, some auxiliary information about the population. This is the entire framework.
So this sampling that we have is the database, right?
Database, yes. Database was selected by sampling from the population distribution.
So is the population the entire database and this is like a section of the database?
Exactly.
Or is it like this is the database and that's like some synthetic?
No. This is a subset of this. This has to be a subset of population distribution. Think about 10,000 people in the population.
No, but the entire database is the population.
Yes, think about some entire database is the population, and the subset was selected from that population. This is this data set.
But then, so how does it matter if it's not in the subset
Yes.
or not? Because either way he has access to some information that's in the database. Right?
Information in the database, not the complete database. Some auxiliary information. We'll come to that. Some information of the database. Some property of a distribution, property of a probability distribution, something.
Why would an adversary want data from the subset and not the population?
No. So adversary's goal is to figure out whether this target individual was in the subset or not. That was his goal.
But why would that be useful?
Yes, it's called membership. Whether a person's data, think about the support vector machine example, whether a model releases this training data, right? So that's it, right? So so it needs to predict whether Zora's data was in the training set or not.
Okay.
That is membership inference. Yeah. So whether it was in the member of the training data sets or not. Yeah, so as I mentioned, it gets some kind of auxiliary information about the population distribution. So now let's go to more details. Okay. Think about instead of our favorite data set, now let's come to a very simplified data set. So data set about n individuals, and think about n training points, and there are k attributes, and all k are secret. So each individual has this kind of secret bits, k secret bits. Second individual also have some k secret bits, right? So all these secret bits we need to protect. Okay, similar thing. So this is the target point which the adversary gets, and it only knows it is either chosen from this data set uniformly, or it is sampled independently from the population. The population distribution has a parameter p. Okay, this the adversary knows. Think about this parameter p is some vector of probabilities, right? So 0.6 is some number between 0 to 1. So 0.6 some array, 0.6, 0.9, 0.3, 0.1, all this. This is some kind of, so this here is like, if there are k secret attributes, this population, this p will also have k numbers, right, between 0 to 1. And adversary knows this. What does this signify actually? Think about whenever for an individual j, right? Think about a person j. When we are creating this database, why are we creating this database? So this bit 0 was sampled with probability Bernoulli 0.6, right? So with Bernoulli 0.6, we sample, we toss a coin with bias 0.6. If it comes head, we put 1. If it comes tail, we put 0, right? So this is how this first column is being generated. So take this 0.6, sample with Bernoulli 0.6 independently for all individuals, and if it comes tails, put 0. If it comes head, put 1. Okay. Similarly, second column, Bernoulli 0.9. If it comes head, put 1. Comes tail, put 0. Similarly, kth column, Bernoulli 0.4, heads and tails, put 0. This is how this data set was sampled from the population distribution. So population distribution is given by this vector p, and the adversary knows this. This is what adversary knows. Someone was asking the question about population distribution, right? So this is what adversary knows. Okay. So now once the data set has been created, a target has been identified. Okay, this is the target. The adversary's goal is to figure out whether this target data set was used to train the algorithm or not. That is the whole game. Okay, so now what kind of question an adversary might ask, right? It can ask for each attribute, there are k attributes, so for each attribute, give me the sample mean. It can only ask aggregate statistics, not particular information, right, that we have mentioned before. So give me the sample mean for each attribute, right? And the algorithm has to give the answer, but it can, instead of giving the true sample mean x bar, it gives some kind of noisy sample mean a, which is closer to x bar. Remember, we have discussed that the error should not be too high, right? So it can give some noisy mean a, which is closer to x bar. And using this information, the adversary now can ask for questions for all the attributes, all the k attributes, right? And aggregate all this information to figure out whether Zora's or target Z was in the dataset or not. That's his goal. So for one example, say the error, right, the noisy mean that has been reported by algorithm is given by this, where if you compute the noisy mean, it is this vector, right? So first there are 2 1s and 2 0s, so mean will be 0.5. Second 3 1 and 1 0, mean is 0.75. Similarly, kth 1 1 and 3 zeros, right? So mean will be 0.25, right? This is the sample mean of this for each column. Instead of returning the true sample mean, the algorithm returns some kind of noisy version. Say 0.5 has been returned as 0.54, 0.75, 0.71, 0.5, 0.49. So a little bit of noise has been added to all the sample means, and it has been passed to the adversary. Adversary know A. So now its goal is to figure out whether Z is in the training data or not. So yeah, we have k queries, right? K queries for k attributes. Think think about each individual asking k yes or no questions, right? So 0, 0 and 1 indicates some yes or no questions. So first column corresponding to one question where the individuals or users can ask only yes or no. So yes means 1, 0 means no, right? And the answers are drawn using this Bernoulli distribution. If Bernoulli Pj is 1, then say yes. If Bernoulli draw is 0, say no. Think about this kind of queries are being asked to different individuals, right? So they can give only yes or no answer, so we can represent it as 1 or 0. Okay, so here is the thing. So each query j in 1 to k is answered within error alpha. So sample mean for the jth query, right? The jth column is x bar j, and reported noisy mean for jth column is aj. So the absolute difference between them has to be bounded by alpha, right? And now, since we are talking about a membership inference, that we have mentioned that, so if error is less than square root n or less than 1 by square root n, then reconstruction attack succeeds, right? But if error is greater than square root n, then reconstruction attack doesn't succeed. But we mentioned that membership will succeed. So here that condition we are putting. So our error will be greater than 1 by square root n. So now you might get confused that I have, in earlier slide I have talked about square root n. Error is square root n and either greater than square root n or less than square root n, right? Here I am talking about 1 by square root n, right? So think about, either we are talking about only count queries, right? How many people, how many female person aged greater than 40 have the disease. These are like count queries. Here we are reporting averages, right? So count divided by n. So these are average queries. So everything gets divided by n. So square root n gets divided by n, and we get 1 by square root n. So basically in this kind of average statistics, reconstruction error will succeed if alpha is much less than 1 by square root n. But if alpha greater than 1 by square root n, we need to see how membership attack succeeds or not. Okay, so this is the setting, right? Any question now? Okay, so let me give, okay, so let me now state the attack, which is given by Cynthia Dwork at 2015. The attack is, the attack I will describe later. So the result is there exists an attack such that when number of queries k is greater than n, that means number of secret attributes is greater than number of individuals. So number of queries is greater than or equal to n, and if alpha is less than square root k by n. Forget about this term, it's called log 1 by delta. If alpha is less than square root k by n, alpha is what? Alpha is the maximum error permitted, right? So now we want alpha to be greater than 1 by square root n as well as alpha to be less than square root k by n, right? We want this. It has to be greater than 1 by square root n, but it has to be less than square root k by n. If these are true, then there is an attack which tells that if the target point was in the dataset, right? That means if the target point was chosen uniformly from the dataset, then the prediction of the adversary, right? Adversary predict that it is in the dataset. The probability of that is greater than 1 by alpha square times n. This is the result tells that this is a true positive case. The target point was in the dataset. Adversary predicts in the dataset with probability higher than this quantity, 1 by alpha square times n. This is like true positive, right? It was there in the dataset. It is predicting in the dataset with this probability. There is another case of false positive also. Say the target point was out, right? It was drawn actually independently from the population, right? It was not even in the dataset. In that case, the adversary predicting in is upper bounded by a number delta. Okay, this is the attack result is given. That the false positive probability is upper bounded by delta. So now this is the success probability, right? This is the true success probability. Right? If it is in the dataset, it says okay, it is in the dataset with greater than 1 by alpha square n. So this is a success probability. In this probability, this membership attack succeeds. Okay, so think about when k equal to 1.1 times n. We mentioned that if k greater than equal to n, then only it will hold. if k equal to 1.1 times n, it turns out this 1 by alpha square n will be around 90%. You can do the calculation and figure out. It will be around 90%. Okay. So put the alpha value, right? Alpha equal to square root k by n. Put it here, and put k equal to 1.1 n. You will get that the probability will be greater than 90%. Okay. So if number of query is 10% higher than the number of data set, right? Number of points in a data set, then the attack succeeds with very high probability, which is 90% probability. So this is a membership attack result.
How about delta, like what kind of value?
Yeah, the delta will set. We need to set delta accordingly. So I have not discussed the attack yet. We need to set some parameters attack accordingly so that the false positive is small. Okay. For now, think about delta is a small value, very close to 0. So here is the attack now. Okay. So attack tells that if A minus P, what is A? A is the noisy mean, and P is the parameter in the population distribution that the adversary knows, right? Adversary compute this quantity A minus P. It also computes Z minus P. Z is the target point. I told you that adversary is given the Z, and it knows P, it computes Z minus P. And these two are vectors, right? A minus P is a vector and Z minus P is also a vector. So it takes the dot product. And if this dot product is greater than some number tau, then it will return that, okay, P is, or say Z is in the data set. If this value A minus P into Z minus P is less than tau, then it will return, so Z is not in the data set, right? So what is basically it is using, right? Think about if Z is in the data set, right? Then the noisy means, the reported means will be, Z will be closer to the reported means, right? Z is in the data set, means are computed using the data set, right? Means are returned and computed and returned using the data set. So the correlation would be higher because Z is in the data set. So now if you take the dot product computes the similarity between two vectors, right? So the dot product will be higher. If Z is in the data set, the dot product will be higher. So it will be probably higher than some good, some appropriately set threshold. Right? So that's the thing. If it is in the data set, it is correlated with other points, and so the threshold will be high. So the value will be high and it will exceed the threshold. Then we will return. It's a simple attack. But if Z is not in the data set, then the correlation with the data set will be low. So the dot product or the similarity with the data set will be low. So it will not cross the threshold. So we will return out. A simple strategy. And it works because this result is for this strategy. So it works with this probability that true positive, the attack succeeds with probability greater than 1 by alpha square n. Okay. And now how to set? We have to set tau accordingly. We have to set tau is square root k times log 1 by delta to make this false positive probability delta. So attack will take delta as a small number as input. Think about delta very close to 1, 0.01. And it would set tau equal to square root k into log 1 by delta to make this false positive probability work. So this is how it will set the tau. And there is some extra bit of information. You can now ignore that. For this to work, we have to choose. So we are told that, okay, this is the population probability, right, for the population distribution, right? This has to be also chosen uniformly from distribution. You can ignore that. So basically the point here is there exists an attack, a membership inference attack, which will work with high probability, a 90% success chance, and the attack is very simple. Okay. A? Yes. Yes. You need to more secret attributes or more number of queries. Even if number of secret attributes is less, you can have much more number of queries. Think about if secret attributes are 3, you can number of data points is 100. You have to make 101 queries.
How does that compensate for there being less?
For?
How does that compensate for there being less secret attributes?
It doesn't compensate for anything like that. But the thing is number of queries. The takeaway here is, I think the question is why we need number of queries has to be greater than equal to n, right?
I want to say, and it seems to me that it's a very unpractical situation.
Sir, guys, the K there, does it mean the number of queries or the K secret attributes?
No, K there means number of queries. So in this example, it is secret attributes. I think I should be more careful. I should not mix it up. Yeah, K is number of queries. Your number of queries needs to be greater than n. Secret attributes can be anything. So yeah, I just wanted to present it simply. So I think there's a misconception here.
A minus B dot Z, what's the intuition behind the attack?
Yeah, so if Z is in the data set, right, then it is more correlated with the output, right, A. A is an output from the data set, right?
If A converts to sample, like the sample mean, if the sample mean is the true mean, then this should be 0, right?
No, yeah, sample mean is true mean is 0. No, why?
Like, I didn't quite understand. Let's say if it's A equal to B, like,
A is not equal to P. P is anything. P is some distribution which is randomly sampled from uniform. A is not equal to P.
P is generating this data, right?
P is generating this data.
So this A is indirectly sample mean, right?
Yeah, there will be always errors, right?
Let's say if it's close to this indirectly, this will become low, right?
Yes, if it is very close, it can become low. But there is always be error, and the error will be of the order 1 by square root n, right? So you think about your sampling n random variables from Bernoulli P, right? Right? And what will be the error?
Large, it should converge, right? So this,
Very large n it will converge, right? But we don't have very large n.
but then why we are greater than or equal to double, like what's the
Intuition is like, given a target point, you have to see what is the correlation with the error, with the output. Forget about P as of now. We can take P this side, forget about P, or re-normalize everything, forget about P. Think about A dot Z greater than or equal to tau 1 naught, right? So if Z is in the data set, so it is much more correlated with A than if it was not in the data set, right? So then if it is in the data set, the dot product will be higher. And to answer your question, A is sampled, A is the noisy mean, right? The data is sampled independently from this distribution. So if you take an average, right? Take a average, the error will be of the order standard deviation. So what is the order of the standard deviation is 1 by square root n. This is Gaussian concentration, kind of concentration inequalities, right? So for finite n, the error will be 1 by square root n. So it won't be 0 for finite n. Okay, so you know the attack, right? So this is a simple attack which will tell that whether Z was the member of a training dataset or not. So this is called membership inference attack. All right, let me now give an example of membership inference attacks in practice. This attack I am calling ML versus ML. This attack will use ML to attack an ML model. So from training dataset, we train an ML model and do all our ML predictions. The attack will train another ML model to attack, the adversary will train another ML model to attack that trained ML model. So this is called ML versus ML. Okay, let me give an example. So we have a population distribution. A dataset is sampled from the population distribution, which is a training dataset. And now we train a neural network from this dataset, right? Think about a classification problem. There are 3 classes, there are number of features, and there are 3 classes: cat, dog, or some human. So given the features, you have to identify between these 3 classes. So train a neural network to do the task. So now there is a prediction API of each model. What the API does? So when you want to predict, right, if you train the model, now you take a test data set and ask what is the prediction, right? Which class it belongs? Does it belongs to a cat or a dog or a human, right? Which class it belongs, right? So in prediction API, it does that. Takes a feature and gives which class it belongs. This is what you are predicting the label of a features of a feature. This is ML. Till now, this is ML. This is what an ML pipeline is. Now there is an adversary which has some information about the population distribution, say some parameters of the population distribution. So how now the adversary will launch an attack on this ML model, right? How it does? So now remember, right? You have adversary have two options. Either a target data set, right? A target point is selected from the training data set, or it is uniform, or it is chosen from the population distribution, right? So what the adversary will do? First, in the prediction API, it will give the features from the training data set and asks the prediction API to predict the label, right? So it take a feature from the training data set and ask, predict the label, and say this is the label that the prediction API is giving. So three classes. Probability of dog is higher. Say blue is dog, orange is cat, and green is human, right? These are the probabilities. With this probability, the data is a dog. This probability is a cat, and this probability is a human. So this is what the prediction API gives. An adversary sees this. Okay. If I take input feature from the training data set, this is the probability. This is the classification I get. So now it takes input features not from the training data set. This is the second option. It has two options, right? Input feature not from the training data set, and ask the prediction API, tell me what is the classification probabilities of these features, right? And the prediction API gives this. This is the probability of a dog, orange probability of a cat, and green is probability of a human, right? Now, see these two, right? Adversary can see these two outputs, right? It recognizes the difference in the prediction. If I give a feature from training data set, I get this prediction. If I give a feature not from the training data set, I get this prediction, right? And it tries to recognize these differences in the prediction, and it does it for multiple number of data points.
So the adversary already knows beforehand which features are in the training set and which features.
It's not like that, but think about as of now, yes. Think about it. It's not completely like that. I will explain it to you later. But think about it. It can get the features from the training data set, right? And it do this.
The input features that are not from the training data set, are they from the population distribution?
Yes, they are coming from the population distribution. Adversary has the population distribution. It samples from there. So what the adversary now do, it now train an ML model, which I am calling attack ML model, based on this predicted classification probability. So now it tells that, okay, if this is the classification probability, I know the input features are from training data set. If this is the classification probability, I know input features are not from the training data set. So now I train another ML model based on this. Okay. So in this ML model, in this new ML model, the labels, the features and the labels got changed, right? So this is now the features of the ML model. Will this it will get trained, and that label will be whether it is in the training data set or it is not in the training data set, right? So this attack ML model, it will take this kind of outputs, right? This classification probabilities as its input and predict whether the data point is whether it was in the training data set or not. So the ML got reversed basically. So this ML model is attacking this ML model to do membership inference. So this is a very big paper by Reza Shokri and co-authors in 2017. But they did, I think in some computer vision tasks, they did this. Okay, so what is the main insight? That ML models overfit on the training data set, right? So if your training, if basically overfit on the training data set, so the classification accuracy will be higher for points from input features from the training data set, and the classification accuracy will be lower for input features not from the training data set. So this information is being used crucially to train ML model and figure out whether a particular data point given feature is included or not. Okay, you understand this kind of membership in practice. All right.
So it basically is based on the library of our fitting, the model or the adversary
Yeah.
can decide whether it's from the population or from the training data. But then we'll have to fix some threshold, and that might need some
Yeah. So
threshold to be.
yes, the attack all leads fixing thresholds and some threshold tunings that the previous example that I've shown, right? You have to fix a threshold, right?
Yeah, but then it's dependent on the data.
Exactly. Those are engineering problems. Yeah, those problems are there. Those are all there. But it turns out that you can fix something. You can They have come up with some thresholds and some schemes to do all this.
So it's more like a surrogate model.
Yes. Yeah, you have to tune those kind of thresholds also.
So, like with this, an overfitted model would be easier to attack.
Exactly.
So is this like some sort of a generative adversary network type of?
No, not like that. But the concept is, yeah.
In that case, like, can we use some like idea like that to train a model to like generate adversarial like cases which are like indistinguishable from the original distribution?
Yeah, maybe, yeah. Don't know. Okay, so I think the last slide is coming up for today. So here is the whole attack landscape. I've bored with you a lot of attacks today. So here is the whole attack landscape. So this is a line which is telling error alpha for releasing average statistics. Okay. So 1 by square root n is one important point and square root k by n is another important point. Remember this slide? Membership attack, we need alpha, okay, the previous slide. Alpha has to be greater than 1 by square root n and alpha has to be less than square root n, k by n. So these two are very important points for us. Yes, so 1 by square root n and square root k by n. If the error alpha for releasing the statistic, that means if the statistics are released with error less than 1 by square root n, then we know the reconstruction attack succeeds. And the attack will require k equal to order of n number of queries that we have seen. If the error is greater than 1 by square root n and less than square root k by n, then we have seen membership attack will succeed with some 90% probability and it will require number of queries greater than equal to order of n that we have seen. This is the whole landscape. So each of the attack needs to succeed with this.
Sir, like in the previous slide, when you used an ML model to learn the classification boundary between these two datasets, how come this root k by n playing a role in determining that?
Yeah, so
Like there, we are not specifically.
yeah, I've not given you the details. Yeah, not details I have not given you, but everything will hold out. Yeah, I think you should go and read Shokri's paper for that. So it's a big details. So I don't want to go to too much in ML in this series. So yeah, so this releasing too many statistics. What does this thing? This tell that okay, if you release too many statistics, order of n number of statistics, with too much accuracy, right? If error is less than 1 by square root n, if you release too many statistics with too much accuracy, then the reconstruction attack will tell that okay, we can determine the entire data set. Similar things for the membership attack. Release too many statistics with too much accuracy, but less accuracy than reconstruction attack, right? Too much, but still less. Then we can reveal the presence of individual data in the data set. These are two, right? Membership attack, you can get the presence of an individual data in the data set. A reconstruction attack, you reconstruct the data. So these are two different landscape of the attack. And these are the boundaries. Okay. So every statistic released, you know that it's some kind of constraint on the data set, right? So you think about this mean example, right? From 3,30,000 to we released to 30, right? The number of constraints get released, reduced so much. So every statistics actually put some constraint on the data set. And so we need a quantitative theory that how much is too much, right? How much error is too much error, or how much accuracy is too much accuracy, and how many statistics is too many statistics. Right? We need a quantitative theory for us that, and that we'll do it tomorrow. Thank you.
Do you have any more questions? Alright, you can call it day.
This will be here, right? Like
Yeah, I'll call the admin. How are you doing on time?
yeah, fine.
Yeah, fine. No, not that. Like, for all this year.
Yeah. So tomorrow I think 3 lecture I don't have. I don't fair about.
Okay.
I have, but I will probably okay. So tomorrow what will happen? I will prove some results. Should I prove or just local? It will might. Then I will need probably the board.
No, you can, you want board and
Yeah, I have some slides to get. I have also